This is Harry Westaway, and I'm here with Mark Stanyon, our Senior Application Chemist. We're going to talk about the thickener technologies of Scott Barder and their applications in formulating household, industrial, and institutional cleaning products. Scott Barder was founded in 1921, and the headquarters established in rural Northamptonshire in 1940. The company was gifted to the employees in 1951, with all shares held in trust, meaning that we cannot be acquired. As a consequence, we were able to take the long view and look to forge partnerships with suppliers and customers. We are technology focused, with approximately 10% of our staff in technical roles, always looking to innovate and can offer custom-made development products. The headquarters is still in Wollaston, England, but today Scott Barder is a truly global company with manufacturing and technical expertise around the world. Now I will hand you over to one of our technical experts, Mark, to take us through some of our thickener products.
Thank you, Harry. We have Texapol inverse emulsions, and we have the Texacryl alkali soluble or haze technologies. The Texapol inverse emulsions are supplied as free-flowing liquids. Texapols rapidly thicken when added to water to allow the dispersed polymer to hydrate and swell. As they are already neutralised, there's no need to adjust the pH unless the application dictates. They are already activated and will thicken an aqueous system simply by addition. Texapols, however, do give a degree of opacity to a formulation. So if you're wanting to formulate a clear gel, this is quite difficult with the Texapol. This picture represents an inverse emulsion particle dispersed in the ore phase. The central core is the hydrated polymer protected by a shell made up of a low HLB surfactant. The oil itself is a high boiling point mineral oil, typically with a boiling range of 200 to 250 degrees centigrade. Our products as supplied typically contain 20 to 25% of the mineral oil depending on the grade. This graph represents inverse emulsions at 2% solution in water. The pH has been adjusted with hydrochloric acid and sodium hydroxide. You can see the viscosity versus pH on this profile is different depending on the composition of the Texapol.
From this graph, would I be right to assume that Texapol 63510 is the most versatile?
Yeah, definitely, Harry. The Texapol 63510 has the broadest pH usage range. However, the actual viscosity of any of these Texapols in an acidic or a basic solution depends on the acid or base used. So something like an organic acid would have less impact on viscosity over and above something like hydrochloric or sulfuric acid. So this is only a guide. You have to take into consideration the acid or base that you're using in your formulation. Here we have a start point formulation for an oven cleaner. The Texapol in this formulation is a technical development. The polymer itself had particular high resistance to the sodium hydroxide solution. But the main function of the thickener was to increase the viscosity, to help keep the ingredients dispersed, but also to aid the cling factor, if you like, of the formulation when applied to a vertical surface like the inside of an oven. So that improves the residency time of the sodium hydroxide, which allows the caustic to break down the food deposits on the inside of the oven, so more effective as a cleaner. Moving on to our Texacryl acrylic dispersion technology. They are divided into two distinct technologies, the alkali soluble emulsion and also the hydrophobically modified alkali soluble emulsions. Both technologies are supplied at 30% solids in water, and they are only active in the alkali pH region, 7.5 to 13, but more specifically 8 to 12. A typical ASE or alkali soluble emulsion, Texacryl 13308, would be regarded as a general purpose pseudoplastic rheology modifier. However, the hydrophobically modified alkali soluble emulsions, such as Texacryl 13313 or 13317, are highly associative in character and generally used to customize the rheology of a formulation. They can also function as a secondary surfactant. To give you an idea of how the association is working to give that customized rheology performance, this diagram shows a typical polymer, the stringy part of the picture, with the association, the green balls, on the end of that polymer. The association, or the hydrophobic moieties, associate with each other, other ingredients in a formulation, to give a pronounced different rheological performance in a formulation. To demonstrate that, I'll put together this start point formulation for a simple abrasive cleaner. So we have water a surfactant, and a scouring aid, calcium carbonate, quite high particle size, typically around the 50 micron region. I made up two formulations, one with 13313 and the other with 13317. Adjusted the pH to 12 with sodium hydroxide, which gave a fairly viscous but mobile gel. Although the two formulations were effectively the same, the rheological performance was quite different. With the Texacryl 13313, you see that we are modifying more the low shear viscosity profile, which gives a perception of high viscosity at low shear, very good at suspending the aggregate, and also very good at clinging to a vertical surface. But with the Texacryl 13317, the formulation was less viscous on standing, but gave a more pronounced viscosity on application shear. So it gave a different perception of the product, not necessarily a different function.
Both Texacryl 13313 and 13317 sound like they give interesting benefits. Is it possible to get the best of both products in one formulation?
It's quite common to use more than one thickener in a formulation to give, for example, a pronounced viscosity at low shear rate to suspend a very sort of high SG aggregate. And along with that, you could use the 13317 to give a more pronounced viscosity at high shear rate. And that would give a different perception of quality in the product itself, or could even actually aid the function, particularly if you're formulating something like a grinding paste or sort of aluminium oxide formulation, where you would want some resistance in the actual paste itself to give a better performance on application. I mentioned earlier a technical development product, the Texipol. Scott Barter prides itself on following up all of its current range with new developments. We work on current established platforms, or we work on new technology platforms, such as the cationic in this particular slide. We have a range of developments around the cationic monomer offering based on the Texipol inverse emulsion platform, which are effective at low pH range, typically 1 to 7. These can be used for low pH systems such as toilet bowl cleaners, limescale removers and all-purpose cleaners, but are also compatible with cationic surfactants for things like car and shoe care and hard surface cleaners.
Thank you, Mark, for the quick overview of Scott Barter's product offering into the formulation of household, industrial and institutional cleaning products. If you're interested in learning more about the products presented, please visit the Smart Lab Direct website, where you will find additional technical information. I'll include a link to that. The website also provides the formulator a direct link to technical experts like Mark for formulation assistance and rapid samples. Thank you for taking the time to watch. Get in touch if you have any requirements in this area, and check out the website and social media channels for news and new product information.